Right, we have looked at building the molecule, and so now we need to move on to doing some kind of calculation. There are two ways we can do calculations with molecules. One is we can use molecular mechanics, which I'll deal with in this lecture, and the second method is quantum mechanics, which we'll explore a bit later on in the course. Now, in terms of molecular mechanics, bonds are modeled using functions that treat them as springs, and of course calculating the energy of the spring is simply dependent on the length of the spring, or how far it's been stretched, and so that calculation is extremely fast. And so if you model a molecule as a collection of springs, you can very quickly get to an energy value. So it's scalable to many atoms, so you can easily do these kind of calculations on huge molecules such as proteins. Now, molecular mechanics calculations can't give you all properties of a molecule, but it's still extremely powerful. You can get things like optimum geometries, you can try and find the most favorable conformation, and we'll speak a bit later about normal modes of vibration. Now, to do a molecular mechanics calculation, we need to calculate the total energy of a molecule, and that total energy is calculated in terms of the sum of bonded terms and non-bonded terms. We're going to, in this lecture, look at the first of the bonded term, which is a stretch term, but there are other bonded terms that we need to explore, like the Benz and torsional energy, and the energy of a molecule is not simply dependent on that, but if there are clashes between atoms, if atoms are bumping into each other, for instance, you may need, if there's some favorable attraction, you may need van der Waals terms or electrostatic terms, which are non-bonded terms, to get an accurate value for the total energy of that molecule. So the total energy is the sum of some bonded terms and some non-bonded terms. So let's explore now the form of that stretch term. The stretch term, the first term in the molecular mechanics energy term. To get a stretch term, we need to just explore how energy varies with a bond. When you've got two atoms that are at their equilibrium bond distance apart from each other, we anticipate that they will have the lowest possible energy. In molecular mechanics, this lowest possible energy contained by the bond is 0 kilocalories per mole. Of course, if you were to displace those atoms, for instance, if you were to stretch them away from equilibrium, you see the new R distance is different to the equilibrium bond distance, which is R0. We expect that that energy will increase. And this increase in energy is a driving force back to equilibrium, because the system will want to go back towards the equilibrium bond distance, because it can release that energy and go back to having the lowest possible energy of that is possible for that bond. Similarly, if you compress a bond and you move it away from equilibrium, the energy should also increase, and you can see the distance between the bond distance is not at the equilibrium bond distance, and so the energy must go up in that case. So how can we find a function that gives us an energy profile like this as we change the bond distance? Well, it's fairly straightforward. We can borrow from physics, from Hooke's law. In Hooke's law, the force opposes the displacement, so you will have a spring constant K, and you will have a displacement X, and if you've got a positive displacement, then the driving force is backwards. If you've got a negative displacement, the driving force is forward, which is why you've got that negative sign. Of course, we don't have X here, we've got our actual bond length and the equilibrium bond length, so of course that difference is the displacement, so instead of X we can include R minus R naught. In terms of the Hooke's law energy of a spring, the Hooke's law energy is a half kx squared, which in our bond terms, if we had a bond force constant, would be a half k to r minus r naught squared. But the convention in molecular mechanics is that we include the half and the k together, and so the energy term for a single bond is a constant, a spring constant that is dependent on the bond. It's dependent on what the atoms are. So different pairs of atoms will have different k's, and they will also have different equilibrium bond distances, but we can calculate the energy in terms of k into r minus r naught all squared. So the question is, if we build up an energy profile based on bond distance that looks like this, how does that match experimentally what happens with atoms as you compress and pull out? Well, the real situation with atoms follows this thin line here that you can see here, which is a Morse potential, and you can see that as we put atoms close together, you can see the x squared potential that we've got from Hooke's law matches the Morse potential really, really well. However, when you try and pull atoms apart, you can see that Hooke's law predicts that the energy will increase quite rapidly, but in reality the energy won't go up so much. It's possible to break bonds by putting atoms far apart, but from Hooke's law, the further apart you move atoms, the higher and higher the energy will get, until that energy is impossibly great. So if you move your atoms too far, the energy will be impossibly high, and the driving force back to equilibrium will be unbelievable. So you cannot break bonds with this energy function we have created. However, when we look at molecules, we're most interested in what's happening around equilibrium, and around equilibrium this x squared potential matches the real case very well. So this function is quite useful to us. One thing that we need to worry about is in a molecule there will be more than one bond. So I've got a hypothetical molecule here which has 5 bonds, and you can see some of these bonds are stretched. They are longer than the equilibrium bond distance, and some of them are compressed. They're less than the equilibrium bond distance. So what we would have to do is we would have to do separate calculations into k into r minus r naught squared for each of the bonds to get an energy value for each of those bonds that we could then combine. We could add up those 5 values to create that E stretched term, which is the energy from all bonds in that molecule. So let's have a look at a simple example. The simple example is water, and in the amber force field, the K is 553 kilocalories per mole per angstrom squared, and the equilibrium bond distance is 0.96 angstrom. So you can see immediately that in this water molecule, this hydrogen-oxygen bond distance is not at equilibrium, and this hydrogen-oxygen bond distance is also not at equilibrium. So the energy from each of these bonds will not be zero, and we can calculate it using this k into r minus r naught all squared. So for the first bond, with its distance of 1.26, we can calculate the energy value of 49.8 kilocalories per mole. And for the second one, we can do the same thing. Notice that the second one is a compressed bond rather than a stretched bond, and we calculate exactly the same energy for the second one, and that's because the displacement from equilibrium for the second one is exactly the negative of the displacement from equilibrium for that one. However, we've now got an energy value for each of the bonds, so we can build up our E stretched term. Our E stretched term, we need to add all the bond values, energy values together, and there are only 2 in this case. And so I've now got the total energy from stretches in this molecule to being 99.6 kilocalories per mole. Okay, so that's the stretch term. There are other terms, underbonded terms, so in the next set of slides we'll have a look at the bend term and how this can be used to complement the energy term in molecular mechanics.